Hello and welcome to today's webcast, Industrial Solids Liquid Separation, Making Contaminants Sink or Float, sponsored by Evoqua Water Technologies. My name is Angela Godwin. I'm Chief Editor for Water World Magazine, and I will be your moderator today. A few housekeeping items before we begin. The slides for today's presentation will be pushed out to your screen automatically. The presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. If you are running any pop-up blocking software, you will need to disable it to view the webcast. In addition, it is recommended that you close down all other applications for better performance. If you have any technical difficulties during the webcast, please type your issue into the Ask a Question box, and a member of our webcast support team will work with you to correct the problem. A certificate of attendance will be issued automatically via email to all attendees at the conclusion of the presentation. Just please be sure to stay logged into the webcast until you see the congratulations message. For your convenience, the presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent out to all registrants with a link to that archive. It'll also be accessible from our homepage at waterworld.com. We have two terrific presenters for you today. Alex McDonald, PhD, is a wastewater business development manager for Evoqua Water Technologies. He has more than 30 years of experience in industrial water treatment, including the design, development, and implementation of water treatment programs in raw water, cooling, boiler, and wastewaters for the electric utility and oil refining industries. Alex has presented at numerous conferences, and he is the author of more than 20 technical and scientific papers and 16 patents worldwide. We also have Chuck Ross, PE. He's the technical director of Evoqua's Organic Wastewater Center of Excellence. He has 37 years of experience in industrial waste management and wastewater treatment, primarily in the areas of physical chemical treatment and biological treatment. In 1987, Ross co-founded and became vice president of Environmental Treatment Systems, a provider of DAF and biological treatment systems, which became an Evoqua brand in 2016. Ross is a member of the Water Environment Federation and an author of more than 40 technical papers and other publications on waste management and environmental monitoring. And now, without further ado, I will turn the program over to Alex.
Good morning, and thank you for the introduction. Our agenda today is first to highlight some of the challenges we face, followed by a technical discussion on two of the most widely used industrial separation processes, clarification and flotation. And as part of that discussion, we'll include some new technologies to give us an idea on where the industry is headed. And then at the end, leave some time for questions. To start off, just a real brief survey, a few questions for the group to gauge interest in specific applications and help guide the discussion.
Yes, Alex, thank you. So folks, you'll see a survey come up on your screen. If you would just take a moment to enter in your thoughts. The question is, what types of solids liquid separation systems do you currently employ? Clarifier, flotation, such as DAF, IAF, DGF, API, etc. Both clarifiers and flotation systems. Filtration with no clarification or flotation. A settling pond, or none of the above. So we'll give folks just a few seconds here to put their thoughts in. You see, we are starting to get some results. Thank you, everybody, for participating. Excellent. Okay, with that, Alex, I will hand this back over to you then.
Okay, thank you very much. Solid liquid separations in industrial wastewater covers a lot of ground. Wastewater streams from an industrial or commercial process may contain a number of contaminants, fats, oils and grease, free hydrocarbons, all of which require, just as an example, all of which require pre-treatment or otherwise have a large impact on the separation processes. Solids to be separated include those precipitated by chemical treatment as part of the wastewater treatment itself, organic solids, either entrained in the process water streams or produced as part of biological treatment, such as an activated sludge unit. These can present real challenges because of the variability of the composition or the low density of the solids formed in these systems. The wastewater treatment often must achieve removal of metals to meet effluent limits, metals which are often insoluble or incorporated into an insoluble matrix. I mean, all of these systems are fundamentally the same, that being the separation of solids from the water, but they require unique considerations when designing and operating the wastewater system. One of the concepts to think about during today's sessions is the basis for selecting the right separation equipment, whether that's a clarifier or a DAF, whether we're going to sink the solid or float them. And I'm not sure whether we're going to be able to satisfactorily answer these, at least in the specific sense. There are just, many unique, often process-specific challenges for each application to be considered. Density of the solids to be removed, variability of flow and composition, and the fate of the solids to be removed, and of course, ultimately, the treated effluent quality guidelines. Cost, capital, operating maintenance always plays a crucial role in wastewater treatment decisions. Evolving environmental regulations are imposing increased demands on existing systems and require installation of new and often expensive technologies. Water costs, or more specifically, water availability, and the cost of sewering are driving change. In many industries, the truth is that wastewater is treated as a cost center. It's not exactly part of the profit-driven process for the plant, and it doesn't compete well for capital replacement or maintenance dollars. Regulatory compliance to meet effluent limits, but also to match process capacity expansion, is a primary driver of spend on wastewater treatment. Examples of evolving regulations, these are just a couple of them, and they do present unique challenges, include new and stringent guidelines, limits for metals, including mercury, arsenic, selenium, to name a few, and coal combustion residual, CCRs, for coal-fired power plants. The demands of meeting evolving regulations, increasing capacity, are also challenging operators of wastewater facilities. New installations, new technologies are increasingly automated, but they still require a trained and skilled workforce. This skill set is often not part of the core competence of the facility owners, and that's true whether it's an oil refinery or a manufacturing plant or a municipal government. Outsourcing a wastewater treatment plant is increasingly a viable option. The next section of our presentation is a technical discussion on clarification. I'll then, at the end of that, I'll turn it over to Chuck Ross, who's going to go on and discuss flotation more specifically. So clarification, a simple working definition of clarification is the removal of small quantity of solids by gravity sedimentation from large quantities of water. Examples include the removal of turbidity as a step in producing drinking water, for example, or settling sludge from a biological process. There's many designs: standard circular clarifiers, flocculating solids, contact, assisted settling designs, inclined plate and baluster floc clarifiers. And we'll just touch on a few of those next. The clarification process itself may include several steps: formation of solids by precipitation, promotion of coagulation and flocculation, and that's often assisted by chemical conditioning or the physical handling within the clarifier itself. and then followed by the separation of the solids by gravity sedimentation. Ultimately, the purpose of clarification is to remove the subtle solids. And handling of the solids, the removal or wasting or sometimes recycling back into the system, is an integral part of that process. The overall design goals of the clarifier are real simply to minimize the solids within the treated effluent or the overflow, and to maximize the solids concentration of the settled sludge removed from the bottom or the underflow. This is a diagram which shows basic structural components of a standard circular clarifier. The influent water to be treated enters the clarifier, and in the design show, it's entering the center well, which incorporates a mixing zone where chemistry can be added to promote solids aggregation. And there's other designs which employ peripheral influent feed as well, and I'll touch a little bit on that in the next slide. The cone structure here in the middle creates a zone to disperse the energy of the influent flow and guide the solids downwards into the outer separation zone where sedimentation can occur. Settled solids are fluidized on the bottom by the mechanical rake, collected in a sump and removed either by blowdown or wasting from a system. And there's other systems as well. There's other designs that employ hydraulic removal of settled solids, such as an Evoqua tow-grown clarifier, and I'll describe a little bit of that later on as well. A key takeaway from this diagram, and basic to all clarifier designs, is that there's a single influent stream and two effluent streams. The treated effluent or overflow, and the settled solids or underflow. These specifications, along with the characteristics and loading of the solids to be settled, these are the primary design parameters which determine clarifier size and configuration. There are many designs, as I mentioned. This is an example of a bridge-supported clarifier with a feed in through the side of the basin and into the center well. Shown here is another type of design, a pier support with feed entering from below grade. Shown here is an example of an Evoqua rim flow clarifier, which has peripheral influent feed and peripheral overflow. And it provides really efficient energy dispersion, which translates into higher hydraulic loading and a small footprint, and then higher sludge recirculation rates. Shown here in the lower left is an example of a hydraulic removal of solids. In this case, it's incorporated into the rig design, and it's an Evoqua tow-bro design. The hydraulic removal of the sludge via this provides a more direct and rapid and uniform sludge removal process. Clarifiers can be upgraded as well to increase capacity, improving solids handling, have the internals replaced or modified. And utilizing the existing concrete or permanent structures at a facility is usually a pretty cost and space-effective option. The process of gravity sedimentation, settling, can be described by Stokes Law. It's a mathematical equation which describes the velocity of a spherical particle settling in water. And it describes it in terms of its basic physical parameters, in terms of its size. In this case, the particle diameter of the particle d in the equation, the density of the particle, and more specifically, the density difference between the particle and the density of water, and also the velocity of the water c. And it's a simplification, but it's a powerful formula that is used for estimating solids settling within a clarifier. The equation guides us on achieving basic principles of clarifier design, and that be to minimize solids in the overflow and maximize them in the underflow. It tells us, firstly, that we can increase settling velocity and therefore the efficiency of settling by increasing the size of the particles. And we can practically accomplish this in a number of ways. Chemical addition, the chemical treatment program, optimizing mixing energy or sludge recycle and that increases solids contacts and encourages flock formation. Secondly, it tells us that we can increase settling by increasing particle density. This can be one example of how we can accomplish this is by ballasting the flock. And for example, Evoqua Comag and Biomag systems utilize magnetite power for increasing settling velocity. The importance of density also highlights the need to optimize coagulation and flocculation chemistry, and also to recognize the impact of water temperature on the settling process. And thirdly, it tells us that settling velocity is inversely proportional to water velocity. Clarifier cross-sectional area must be matched to the demands of the hydraulic flow and the solids loading. It is significant to note the impact of settling velocity on clarifier size or footprint. Ballasted clarification combined with plate or lamella-assisted settling can deliver solids removal from an equivalent hydraulic flow in a fraction of the footprint of traditional circular designs. Of course, there's many other practical considerations, starting with proper design of the center well to accommodate, variations in hydraulic load, variations of flow. And it needs to efficiently dissipate energy, minimize turbulence, as well as encouraging flock growth. Another consideration is the proper design to handle solids, to keep the flock bed fluidized and reliably remove them from the system, minimize bridging, formation of septic zones, and these factors in the solids handling. And also another consideration is because the settling process is imperfect and it's variable, is the proper design to remove and manage scum and float, which can sometimes accumulate on the surface of the clarifier under some conditions. And shown here, in this photograph, it's just one design, and there's many. And this is a standard skimmer, and it's got an anti-rotation scum baffle. When we go to design a clarifier, state point analysis can be used as a valuable tool. And it's an example of a tool that we use. It's useful for designing and operating a clarifier to handle hydraulic and solids loading for settling of biological solids with an activated sludge unit or an ASU. In state point analysis, the three flows are considered: the total influent, and then the two effluent streams, the overflow, shown here in green, and the underflow, shown in red. This is a graphical representation of state point analysis. This is a graph on the vertical axis of solids flux, and that's the pounds of solids entering the clarifier per cross-sectional area. And on the horizontal axis, the concentration of biological solids entering the clarifier. The settling flux curve, that's shown here in yellow, is unique to the solids in the system. We usually determine this curve empirically. We collect a sludge sample from the effluent of the aeration basin, and we measure the settling velocity for various concentrations of that sludge. We can also estimate it from a settling volume index and calculate it, but usually collecting a sample and doing the test in the field is the most accurate way to do that. This green line is calculated from the overflow rate, and this red line is calculated from the underflow. The point at which they intersect is referred to as the state point. For proper clarification, the state point needs to be underneath the flux curve, as shown here. This type of calculation, it's useful. We do this to determine the maximum overflow rate and the maximum solids concentration that a clarifier can handle. An example of how we would use this to demonstrate it is shown in this next example. And this is another example. The second green line, we've increased the flow rate to twice the overflow rate. Increasing the solids flux in the overflow and the underflow moves the state point outside the curve. This predicts that under these conditions, proper settling would not occur and that the solids would be carried over in the overflow. This is an example of the type of design calculation we would go through. State point analysis is a useful tool for matching clarifier design with operative conditions, for establishing mixed liquor suspended solids targets, in this case for an activated sludge system, for a given hydraulic flow in order to achieve proper settling and hence effluent quality. It's important for us to realize that these are dynamic, okay? They're changing. Variations in the solids characteristics occur in the natural course of operation. For example, due to changing COD loadings, conditions that promote filamentous growth, changes in sludge age, all of which occur in the normal operation, can shift the flux curve and impact settling. These variations are considered, and we do consider them, as part of the clarifier design process. Shown in this table are just some typical average operating ranges of overflow that we use for design purposes, and they're for various clarifier designs. These operating overflow rates and the solids loading define the size, the footprint of the equipment required. And clearly, overflow rates achievable in modern ballasted or plate lamella type clarifiers are significantly higher than traditional circular designs, and they translate into much smaller equipment and increased tolerance for variations in hydraulic load under real-world conditions. Evoqua's COMAG and Biomag systems utilize magnetite to ballast flow. This results in higher settling velocity, enhanced clarification, in a much smaller footprint. Mobile and permanent systems are available for both of these technologies. The magnetite powder is hydrophobic in nature and is actually embedded into the flock and increases the flock density, decreases the sludge volume index, and increases settling velocity. A typical Biomag installation is a retrofit of an existing activated sludge unit. Magnetite powder is introduced into the RAS, the return activated sludge, and it embeds into the flock within the biological aeration basin. The magnetite is recovered from the wasted sludge and then reintroduced back into the RAS. It's interesting to examine the impact of the ballasting process on clarifier design demands using the state point analysis. Going back to this same model, the increased density of the ballasted flock moves the flux curve higher, here shown in white. The state point at the higher hydraulic loading, which was previously outside the unballasted flux curve, is now well inside the design and operating limits. This demonstrates the impact of increased settling velocity on clarifier performance. Higher hydraulic loadings as well as higher mixed liquor suspended solids are possible. A Biomag retrofit will typically double the hydraulic and solids handling capacity of an ASU unit, an activated sludge, as well as, on top of that, improve effluent quality. Well, that finishes up the technical overview I had on discussion of clarification, and I believe we have another set of survey questions just to help guide some of these discussions. So I'm going to pull that up.
Thank you, Alex. Yes, that's correct. We would love our audience input once again on a poll question. The question is, in what area can your clarifier performance be improved? Your choices are improved solid settling rate, improved water flow capacity, reduced solids carryover, reduced maintenance demands, or all of the above. If you could just take a moment and share your thoughts with us, we would appreciate that. Thank you. I do see some results starting to come in. Excellent. Great, thank you. Alex, I can hand this back over to you now then.
Okay, absolutely. And, all of the above. And certainly we see that a lot in a number of applications in terms of improving solid settling rate and reducing solids carryover. And that's true. In the example that I used in the activated sludge unit and the biological unit, we see that a lot, but also in other applications. And it's really a reflection of some of the economic forces that are driving the industry. A lot of plants have expanded capacity, and the capital dollars haven't been spent on a corresponding expansion of the wastewater facility. So you end up with increased hydraulic flows, you end up with increased contaminant loading, and all of that leads to these things in terms of potential for carryover, variability in hydraulic flow as well. A lot of traditional systems don't react well to variations in flow and to variations in loading. And so a lot of our focus has been on technologies that go in and retrofit, rehab, or retrofit existing equipment to increase the capacity to handle those loads. I'll go ahead and turn this over to Chuck Ross now, who's going to discuss flotation, air flotation technology. Chuck, can you take that away?
Will do. Thanks, Alex, and welcome everyone to the dissolved air flotation portion of this webinar. Alex is focused primarily on the gravity clarification, which is getting contaminants to settle. Dissolved air flotation, or DAF, or DAF, is the exact opposite. We're trying to get things to float. As a treatment technology, dissolved air flotation has been around a long time, at least 50 years. It's not as old as a technology as gravity clarification, but it is fairly mature. It is most commonly recognized as a pretreatment for the removal of suspended solids and oils and greases from industrial wastewater, but is also used for secondary clarification and thickening of biological solids, and as a tertiary treatment for the removal of algae and phosphorus and many final discharges. The main principle of dissolved air flotation is the creation and controlled release of fine air bubbles, which attach to contaminant particles that rise within a flotation cell or tank for removal. Now, DAF systems come in a variety of shapes and sizes. They can be circular or rectangular. This is a rectangular unit here. And they can be shallow or deep. Some systems have plate packs, some do not. Regardless, they all possess the same basic features. First, there is a contact chamber, which is where the influent comes in with the contaminant particles, and they make contact with the fine air bubbles that are being introduced into the contact chamber with wastewater. That's where the majority of the attachment takes place between the particle and the air bubble. Next, there is a flotation cell, which is the surface area within the tank where the bubble particle matrix will float to the surface and form a float layer on the surface. To remove that material that's floating on the surface, there is a skimmer system. In this case, it's a flattened chain system that pulls the material across the surface of the water, drops it off into a hopper, and from there it's pumped for either dewatering or disposal. Contrary to popular belief, not everything floats. Lots of things will settle. So there is, DAFs have a mechanism, either a hopper in the bottom with drain ports, or in this case, we're showing an auger that pulls the material as it settles to the bottom. It pulls the material to the front end of the DAF, and then it's being discharged through a port in a blowdown scheme. Now, once the solids have settled and the solids have floated, hopefully more floating than settling, there has to be a means of separating that clarified effluent from those solids, and there's a baffle system within the DAF that carries the flow around through an effluent weir system, and then for discharge of the clarified effluent for direct discharge or further treatment downstream. And all DAF systems have a means of introducing air into water. Basically, it's being forced into solution with the water and releases the air in the form of fine bubbles into the wastewater stream. Because of the white color imparted by the fine bubbles into the water, we call this a whitewater system. Illustrated here is a recycled whitewater system that uses the clarified effluent exiting the DAF as the solution stream. And that as that whitewater is being generated by the pump and the air injection, it's being introduced into the contact chamber where it makes contact with the influent solids coming in. So the key feature of any DAF is the whitewater system, which uses pressure and mixing energy to force air into solution with water, typically, as demonstrated earlier, a recycle stream from the DAF effluent. The key takeaway from this slide is that air solubility in water is affected by both pressure and temperature. The amount of air that goes into solution is directly proportional to the pressure exerted on the solution. The higher the pressure, the more air that goes into solution, basically. This pressure is provided by a recycle pump, which operates somewhere between 50 and 100 psi. Also, as you see in this slide, the wastewater temperature also plays a role in how much air goes into solution. The higher the temperature, the lower the solubility of air in water. So when whitewater is injected into the contact chamber of the DAF, the pressure rapidly changes from something like 100 psi down to just a few psi, and that releases the air in the form of those very fine bubbles, or whitewater. And those bubbles are typically in the 10 to 100 micron diameter range. The size of the bubbles is important since on a mass basis, smaller bubbles provide more surface area for particle attachment. Also, larger bubbles can rise too rapidly to the surface, detaching from the particle and causing agitation on the surface, which is not good from a flotation standpoint. So it's really important that the whitewater system generates and releases only fine bubbles into the contact chamber of the DAF unit. There are basically two different types of whitewater systems. The more traditional involves pumping through a tank and injecting air, compressed air, under pressure. This requires a compressed air supply and a fairly large pressurization tank, usually greater than a minute of retention time. These systems tend to operate in a lower pressure range of 50 to 60 psi, so the saturation efficiencies tend to be lower. However, over the last 20 years, many manufacturers, including Evoqua, have shifted to air handling or DAF pumps, like the Evoqua Hellbender pump illustrated here, where air and water are combined together as they go through the pump. And due to the mechanical energy of the pump and the higher operating pressures, which are typically around 100 psi, these pumps tend to produce higher saturation efficiencies. So with those higher saturation efficiencies, these systems require a lower recycle flow rate to produce the same amount of dissolved air compared to a more traditional system. So there is that increased saturation efficiency allows for a lower recycle rate, which means there's a lesser hydraulic load on the DAF system, which makes the DAF smaller. These DAF pumps can also use ambient air drawn into the pump, which removes the need for a compressed air supply. Now, there are a number of design conditions to consider when looking at a DAF application, but the major ones are these: hydraulic loading rate, or HLR, solids loading rate, or SLR, or the air-solids ratio. The hydraulic loading rate is basically the incoming wastewater flow in gallons per minute divided by the surface area of the DAF, which is the length and the width of the flotation cell in square feet. So most DAFs operate within a range of 1 to 5 gallons per minute per square foot of surface area. The solids loading rate is calculated similarly by dividing the solids mass of the suspended solids and oil and grease coming into the unit through the incoming flow in pounds per hour by the DAF surface area. DAFs typically operate within a range of 2 to 20 gallons, 2 to 20 pounds of solids per square foot per hour. Lastly, we have the air-solids ratio, which is the mass of air provided by the whitewater system relative to the mass of solids entering the DAF with the incoming flow. The range for that is usually in the range of 0.005 to 0.05 pounds of air per pound of solids. Now, as you can see, there's a great deal of variability in these design criteria, and it's due to a wide variety of reasons, which include the type of wastewater that's being treated, the treatment targets, what kind of effluent quality is required, and whether or not chemical conditioning is used. Is a coagulant required and a polymer for coagulation flocculation. All of those play a role in establishing the sizing of a DAF unit. Some contaminants like petroleum and animal fats and vegetable oils float quite easily with or without the dissolved air. Other contaminants like biological solids and paper mill fines can settle, but also easily float with dissolved air and some chemical conditioning. Even metal contaminants like zinc and nickel can be removed through DAF when chemical conditioning is used. In short, the sizing of a DAF depends heavily on the application. So let's take a look at some of these applications. As mentioned earlier, the most common application is for the removal of suspended solids and oil and grease to meet a sewer discharge limit. A lot of DAFs go in to industrial facilities like meat and poultry plants, food facilities, laundries, things of that sort, simply to meet sewer discharge limits on oil and grease. In other applications, DAF is used to recover material for beneficial use, like removing chicken fat from poultry processing wastewater for use in animal feed, or removing contaminants from a natural gas fracking facility to generate water for reuse. Flotation is also becoming more commonly used for clarification of biological solids, like those coming from an activated sludge system or a moving bed biological reactor or just an aerated pond effluent, and even anaerobic systems where clarification of biological solids is necessary for effluent quality downstream. In recent years, we've been seeing a lot more applications for tertiary treatment where phosphorus removal is important. Even DAF systems going downstream of membranes where phosphorus removal can only be accomplished through tertiary treatment using a DAF. And in small municipalities and large industries where there may be large lagoons and algae is a problem and algae removal is required using a DAF technology. What I've shown here is an example of a DAF system at a processed food facility in Texas. The effluent from the plant comes through a lift station, goes over a screen for removing trash and heavy solids from the plant, and then it is transferred to an equalization tank where the contaminant load and the flow is equalized prior to treatment. This is also where pH control is affected, where they control the pH to facilitate better flocculation downstream in the DAF. Flow comes from the equalization tank, goes over through the flocculation tube, where a coagulant is added in addition to a polymer to flocculate the particles before entering the DAF, and within the DAF, that's where the flotation occurs, and the float material is removed. It's taken over to a solid storage facility where the solids can be decanted, free water can be decanted from those storage tanks, and the solids are then taken away for reuse at a local rendering facility. The effluent from the DAF then passes through a pH monitoring and control system to keep the pH within the permit limits of the municipality, and then it's discharged to the city sewer. This is the performance results of this particular facility in Texas. The TSS and oil and grease concentrations coming out are fairly typical. TSS is less than 100 milligrams per liter, and the oil and grease is less than 20. And the removals are quite high in this instance because of both the high TSS and oil and grease concentrations. But the removal percentages are typically greater than 90% for either suspended solids or oil and grease. In this particular case, the BOD removals are also quite high at 80%. I wouldn't consider that typical, but in this case, it's occurring simply because the suspended solids and oil and grease make up a majority of the BOD concentration within the wastewater. So the question gets down to, so how do you know how to size a DAF? Mostly it involves applying the design criteria we mentioned earlier, like hydraulic loading and solids loading and the air-solids ratio for a specific application. For example, a DAF at a poultry processing plant may have a solids loading rate of 8 to 10 pounds per square foot per hour. But for algae removal, you may require a loading rate of only 2. So in most cases, bin scale testing or pilot testing is used to determine DAF sizing and performance. In other cases, industries or municipalities may lease a DAF system to determine effectiveness and provide temporary treatment, while a permanent system is designed and fabricated. Most of the rentals from Evoqua's DAF fleet is used in this manner. Basically, a DAF goes in to demonstrate the performance and the design of a permanent system, and then as the permanent system is being designed and fabricated, then the DAF remains in place until it's ready for installation. So in closing, DAF is a very versatile technology. It's mature, but it is very versatile. It's used in a wide range of applications within the industrial and municipal applications. Before we move on to our summary, I think we have one last survey question on survey question number 3.
That's correct, Chuck. Thank you very much. We would like to ask our audience once again for their input. The question this time is, what's the biggest challenge with your current clarification or flotation system? If you could take a moment and make one of the selections. Your choices are meeting current effluent guidelines, managing varying water flows or varying solids loading, managing increased flows due to production increases, operation and maintenance with limited resources, or obsolete or no automation monitoring capability. If you would just take a moment and let us know your thoughts on that one. And while you're doing that, I would just take a quick moment to remind you that if you would like to ask a question to our presenters, you can do so at any time. You still have an opportunity to do that. Just click the Ask a Question box in your console. I do see some results starting to come in here. Excellent. So, Chuck, I'll just hand that back over to you then.
Okay. It looks like a lot of the issues that are out there are relating to varying flows and contaminant loads, which is pretty typical. It's always a challenge with the DAF system to maintain a reasonably constant flow through the system to get the optimum performance from the system. Okay, in summary, Alex and I have reviewed a number of guiding principles for and the applications of gravity clarifiers and DAFs. It is clear there are many things that can impact the performance of these systems, which includes varying flow rates and contaminant levels, which was indicated in our survey, inadequate chemical feed for flocculation, and insufficient operator attention. It is also clear that choosing a solid-liquid separation system is very application-specific and driven by the type of contaminants being removed. While clarification and flotation technologies are fairly mature, there are a number of recent advances over the last few years, like Evoqua's Comag and Biomag systems and the Hellbender DAF pumps that we employ, which can result in higher performance. All of this points to the need to reach out to an expert to properly design and operate these systems. That's all we have on the presentation part of this webinar. Thank you for attending, and we look forward to your questions.
Thank you very much, Chuck. I will pop in here to help facilitate with the question and answer period. As I mentioned before, just a quick reminder, you still can ask questions. It's the Ask a Question button in your console window. But we do have quite a few lined up already, so we will jump right in. And Chuck, I'm actually going to start off with you. So the question is, how do you determine if you should install a clarifier versus a DAF?
Alex may have to jump in on this one a little bit later, but I'm a little bit biased because I am a DAF person, but it depends on the application. If you're dealing with very heavy solids that readily settle, then a clarifier is probably the right approach. But a lot of solids even solids that you don't think will float. And if it's an application that requires a smaller footprint or a thicker, more concentrated solids, a DAF will typically produce solids anywhere in the 2 to 10% total solids range, which is going to be fairly, an order of magnitude higher than what you would get off a gravity clarifier. Then DAF may be the right technology, especially if you're dealing with wastewater that has a lot of oil and grease, which is going to float anyway. So if you have a lot of material that's going to float anyway, I would tend to look at a DAF as the appropriate technology. Alex, what do you think?
Yeah, Chuck, that's a simple question with many answers, but I think you address all the key points there. But it's at the extremes of particle density, very low density, mostly biological solids. Choice of the DAF and is a little clearer, and then heavier, denser inorganic solids. But both those extremes, the process design is pretty straightforward. And where we run into challenges is the whole gray area in between. If we start looking at effluent quality, look at the sludge handling requirements, and cost and footprint, variability of flows, a number of those factors. So it's I'm not sure if that's a real satisfactory answer, but that kind of band in the middle becomes very, very process specific. That when we go to look at the application engineering considerations, there's a whole litany of things we look at, and mixed solids as well present some challenges. But these are things we address as part of the individual design for systems.
And lots of times within those gray areas, we can do treatability testing to determine which is more appropriate technology.
Terrific. Excellent. Thank you, guys. All right, the next question, Alex, I'm going to pose to you. and that is, what's the best way to address solids carryover from my clarifier?
Yeah, that's another real simple sounding question that's got some long answers, but we'll look at it in various points of view. Depending on the type of system, we'll tend to look at a holistic approach. We'll look at upstream processes to see how it's impacting the clarifier performance, whether it's a variability in load or variability in hydraulic flow. And if it's a system that's got a complex wastewater that's a composite of many streams, we look if segregating a single stream results in improvement of segregation as settling. So that's kind of like the back end of it. The actual clarifier itself, variability of flow is a big deal in systems. The fact of the matter is that we operate our plants to match a process requirement in the plant, and we can't dictate to them a flow or a loading on the clarifier. And so some ability to handle variations in hydraulic load and how it results in carryover. So we look at methods of that, and of course we mentioned one technology, but there's other ones that address upgrading clarifier like Biomag to handle higher solids loading, at least in a biological system. We'll look at modifying scum and float handling processes to handle short term. And often, and it depends on the process, but sometimes if it is a short-term seasonal variation and carryover, we'll look at doing some post clarifier polishing, often with a DAF, particularly if it's solids that are unique to a process that results in short-term floating of solids within a clarifying. Using a DAF as a post-polishing step can sometimes be a real cost-effective way of addressing it. And then, of course, just on a boots-on-the-ground basis, we look at operational factors because operation of these systems has a big impact on when carryover occurs and when incorrect settling doesn't. So that's kind of a hodgepodge answer, but that's a complex question.
Great. Okay, thank you very much. Chuck, let me come over to you here for the next question. The viewer says, I see SS equipment. Is there ever a concern with using SS with oil field produced water? High chlorides, high TDS?
DAFs are used on oil field produced water. We have units out there currently. High chlorides are mainly a concern in two ways. One is high TDS can affect the solubility of air and water, but usually that is not critical. It just depends on the concentration. High chlorides can have an effect on the materials of construction. There are a variety of different variables that go into selecting those materials of construction, whether it's stainless steel or carbon steel or a variation of that as far as materials of construction. And that's the main thing that you have to look out with when it comes to produced water.
Thank you very much. Alex, you're up next. And the question is, can I recycle water from a clarifier or DAF, and how do I do that?
I'm not 100% sure if that's referring to reuse or recycle back into the system if for whatever reason the effluent doesn't meet requirement for the downstream effluent quality. But nonetheless, that's a real common thing. More and more we're seeing reuse requirements, and as long as the clarifier is producing effluent quality, namely TSS or suspended solids, that meets whatever that downstream use is, it's very common. We will sometimes use post clarifier or post polishing in the way of filtration, or even sometimes membrane microfiltration, in order to reduce the solids for reuse. And we have a number of number of applications and a lot of interest in recycling water back to the beginning of the plant, either for boiler feed water or an RO application, or service water. Recycle is also used as water. Very often can be reused just with solids reduction, and so that's very common. As far as segregation of streams after clarifier DAF, again, most this speaks to the holistic design of wastewater plants, and will often be required to either segregate or recycle flows back into the process if for whatever reason the effluent quality isn't met on a short-term basis. I hope that's answered the question.
Great, thank you very, very much. Appreciate it. Chuck, here's a question for you. Do you find EQ sizing or pH adjustment to be more critical to proper DAF operation?
Can you say that again, please?
Sure. Do you find EQ sizing or pH adjustment to be more critical to proper DAF operation?
Actually, both. I mean, adequate pH adjustment is required for good flocculation downstream. If the pH is out of balance relative to the coagulant being used and the flocculant, flocculation will be impeded. So it is critical, and equalization is critical also because it is not just for flow equalization, it's also for contaminant loading, which also can affect the chemical dosing. So I would say they're both equally important.
Okay, great, thank you. Alex, here's a question for you. The viewer is asking about the recovery of magnetite and wondering what is the general efficiency of that?
Yes, in the Biomag as well as the COMAG process, the magnetite is recovered. It's recovered in a magnetic drum separation process from in the case of Biomag, from the biological sludge. It's recovered from that as part of the wasting process, so that you waste the biological sludge. You do not waste significant portions of the magnetite. In the case of the COMAG, it's separated from the inorganic solids and kept within the system. Typical recovery rates are anywhere from 95 to 99%. It's a little bit dependent on loading, but that's pretty typical in a system that's, once it's charged and running at steady state, the makeup rate for magnetite to fresh magnetite into the system is very, very small on a daily basis.
Okay, great, thank you. And I think we have time for one more quick question. We are getting close to the top of our hour together, but let's try one more quick one. Chuck, do you work with UF membranes as polish to your DAF unit?
We do not directly, but others within Evoqua do. And you're seeing more applications where people are trying to put UF membranes downstream. There is a challenge, especially in applications where the BODs are still quite high, which can lead to increased fouling of the UF, and also any coagulant or polymer that's used for flotation, prior to flotation, that can carry over and create fouling issues with the UF filter membrane.
Okay, great. Thank you very much. All right, I think with that, we may want to start wrapping up. We are, as I said, getting to the end of our hour together. We want to be respectful of the time that you all have put aside to join us. So I want to thank you all for the terrific questions. And I want to just let you know that if your question did not get addressed on air, rest assured we will share the entire list of questions with the presenters today, and they will perhaps have an opportunity to answer those questions offline. So let me just thank everybody on behalf of Penwell Corporation. Thank you to today's speakers, Alex McDonald and Chuck Ross. Terrific job, gentlemen. And I also want to thank our sponsor, Evoqua Water Technologies, for the presentation you saw today, which was called Industrial Solids Liquid Separation, Making Contaminants Sink or Float. Quick reminder, the presentation that you saw today will be archived within 24 hours, and it can be accessed from the homepage at waterworld.com. A reminder email message will also be sent out to all registrants with a direct link to that archive. And finally, we want to thank all of you for joining us today. We look forward to serving you with future webcasts. This concludes today's presentation.